We're in section 4.5 talking about integration by substitution. Have just a few problems left to do in this section. Let's see. I believe we're on example 5. Does that look right to you guys? Yeah? Okay. Now if you'll remember, the whole goal in this is to try and figure out which piece looks like it's an inside function, so that when you figure out what's inside and you take its derivative, it is the other piece of what is on the outside still being multiplied by. I think, okay, I'll put it at the end. I think my numbering's got off. It's all right, we'll put it in right here. You get us a backdrop that's not so glaringly white. How about green? I'll do green today. All right. So I believe your number 5 actually says f prime of x equals secant squared of 2x. Is that what it says? Yes? Oh, good. The directions above say find an equation is what it should say. Find an equation for the function f that has the given the given derivative, and whose graph passes through the given point. So it also gives us this point, ordered pair, pi over 2, 2. Does that look right? Okay. So we're supposed to find the antiderivative and find it exactly, not just find an approximation for it with the plus c on the end. Okay? The plus c finds us a general antiderivative. We're supposed to be finding an actual antiderivative on this. So we're going to take the antiderivative, and as we do that on this particular problem, you'll notice that the angle inside here is 2x, not just x. If it were just x, we'd be fine, good to go, no problem. But this one's 2x. So this is technically a u substitution problem. The u would be the 2x on the inside. Now the reason I say this is technically what it is because the more comfortable you get with the antiderivatives, the less likely you are to actually use u substitution here, because you'll just recognize what happens. So like, let's take a look at this one from a truly it is a u substitution standpoint. What's the derivative of 2x? It's 2. Not antiderivative, derivative. 2, yeah, first. And it's 2 dx. We talked about that last time too, right? This is du dx equals 2. And we just move the dx to the other side. So obviously there is no 2 in this particular problem by the secant squared on the outside, right? But it's just a 2. It's a number. It's a constant. There's nothing wrong with this being able to be divided to the other side. So as you're taking a look at this, what you actually end up having is you end up having the 1/2 in front. You still have the secant squared. And then instead of 2x, you have u and then du. And this notation got left off when I rewrote it in here originally. Sorry about that. So this piece dx gets replaced with the du and the 1/2. So far so good? Now, I know many of you are still working on the antiderivative quiz, and so some of you are still struggling to remember, but do you remember what the antiderivative of secant squared is? Tangent. That's correct. And it would be tangent of u and then plus our c. So this then would be 1/2. The tangent of u would be the tangent of 2x plus c. And then what we're supposed to actually do is to figure out what in the world is c. Now when I did the antiderivative on the left, I didn't actually write it out, but the antiderivative of f prime would be f. So I've got f of x on the left. I've got a version of the general antiderivative of that plus c on the right, and then I can use this information and the ordered pair that I was given to evaluate. So I can find f of pi over 2 equals 1/2 tangent of 2 times pi over 2 plus c, and it says this should equal the y value of 2 from up here, right? So obviously the pi over 2 and the 2 in the middle there multiply to give you just tangent of pi. I've got my plus c equals 2. Now what is the tangent of pi? Does anybody know? It's 0. Yeah, it is 0. On the unit circle, Pi is over here on the left, correct? And tangent is sine over cosine. The sine value is 0. It's the y value, right? It's the y value right there. And the cosine value is 1. So this would be 0 over 1. It's 0. So this whole piece right here is 0, which means that you know that c is 2, right? So your function, f of x, can be found precisely, exactly, specifically, whatever word it is that you're using in the context. So this is the tangent of 2x plus 2. And there's nothing special about the fact that this is trig. I mean, we could do this with something that was a polynomial too, right? Sure, it just means that at the very end, you can actually figure out what c is because you're given an ordered pair for you to evaluate it out. All right, everybody good? All right, we're going to go back to ones where we're finding the general antiderivative. I think, do I have these in here? What happened? Where did all my stuff go? That's not the right one either. Hang on, I may need to use another blank slide. That one and that one are yet to come. That one's in there a second time. Man. All right, hang on a second. All right, so number 6 is very interesting, and there's a good reason for that. What do you notice as you're taking a look at this particular one for number 6? First of all, what does it look like is underneath or inside of something else? What does it seem like you would be? Yeah, it seems like it should be 2 minus x. And it is going to be 2 minus x. That's actually going to happen. The weird thing is, what's du? Yeah, it's negative 1 dx. Now here's the weird thing. This part's u, that's fine. But there's still an x in my problem, isn't there? That's not so fine. I can't just replace some of the x's. I got to replace all of them. So here's what we do. You have a relationship here that tells you how to change u into x. Can you solve this equation instead for u for me? What is it? So I didn't mean for you, for x for me. No wonder you're looking at me funny. Sorry, I only see a portion of my screen at a time, but yes, for x for me. What does this equation solve for x for me? 2 minus u, right? Okay, so I know that I've replaced this part that I've underlined in blue with u. That's fine. And I know that I can replace my x now with 2 minus u. The 1's not a problem. It's just a constant, right? So that's okay. This is still underneath the square root. The dx gets replaced with negative 1 du. So as long as I replace all my u's, I'm good with that. Now you might be looking at it and thinking, but how did that help me? I mean, before I had, uglier things underneath the radical. Now I've got an uglier mess on the outside of the radical. What is the benefit to doing that? Well, the benefit is that when you have a single value underneath a radical, like u, and you write it as u to the 1/2, which we're going to do, it can be combined with the items on the outside. If you've got a quote, I didn't use the word right either way. If you have a sum or a difference underneath the radical, you can't do that. It doesn't work. Things are messy. So we like having a single variable underneath the radical, and that's why we did that. So on the outside right now, this is 2 minus u plus 1. So what does this actually give me? Three minus u, and I'm going to go ahead and multiply it by a negative. So instead of 3 minus u, it'll be negative 3 minus u, or u minus 3, right? And then I have u to the 1/2 du. Everybody good so far? Okay, fantastic. Now I can actually distribute this u to the 1/2 through the u minus 3 term, or factor. So this is u to the what? What happens when I have u times u to the 1/2? Somebody said u to the 3/2, and that is correct. All right, this is a 1, that's a 1/2. You add them, 1 and 1/2 is 3/2. Minus, and then I have 3 u to the 1/2 du. I distributed the negative 1 through here and switched my signs. This was it was 3 minus u. and then I multiplied it times -1, so I got u minus 3. So I combined those two pieces to get the u minus 3.
Why was it du times -1?
It doesn't matter. It doesn't make any difference. Dividing by -1 and multiplying by -1 is the same thing. So I can change this to say dx equals -1 du. All right, what's the antiderivative of u to the 3 halves? Are you guys awake today? Okay. Okay, so it's u to the 5 halves, and then what did you want? Times 2/5. Right, divided by 5 halves or times 2/5. The 3u to the 1/2. Well, u to the 1/2 will become u to the 3 halves, right? And it'll be times 2/3. So this will be 3 times 2/3, or just 2. And then plus my c on the end, right? So this is 2/5. I'm not really supposed to leave it with u in it, though, right? Because u is not how it started. So the u can be replaced now with 2 minus x to the 5 halves minus 2 times 2 minus x to the 3 halves plus c. Now, it's possible that WebAssign will take this just fine. It might not, though. What kinds of things might it expect you to do if it doesn't like this version of this? There's a couple of things it might expect. All right, so right now it's 2 minus x to the 5 halves, right? So let's do something before we do the fact. Oh, I think I know what you're talking about. You're saying that there's a u minus, these pieces are in both pieces. Is that what you're saying? That's true. That's a different way of thinking about it than I was going to, but that works just fine. If you've got u to the 5, or you've got this value to the 5 halves and this value to the 3 halves, there's at least a 3 halves in both of them, right? Yes, 5.5 is like 3.5 plus another one. So I think that's a good plan. Let's actually pull out the 2 minus x to the 3 halves then. That leaves me with 2/5 here. And it leaves me with a 2 minus x to the 1 on the first one, right? Because if you take 5 halves and you remove 3 halves, you have 1 left over. Minus, I have a 2, and that's all I have left from the second piece. I think that's a very nice way of doing it. Good thinking. Well, this is one way to do what I was going to suggest, and this works better than the suggestion I was going to make. We're about to do something else that I'm going to suggest and I would expect to see. How'd the problem start out? Radicals. Does our problem have radicals in it at the moment? No. So we need to put the problem back in radical form. So the nice thing, the reason I say this is the nice thing is the part that's in those square brackets doesn't have any radicals in it. It's nice and clean by comparison, so that's actually a really nice way to get rid of the radicals all at once. So this is the square root of 2 minus x cubed. Over here on the other portion, we're going to distribute and clean up. So 2/5 times 2 would be 4/5 minus 2/5 x, and then minus 2. So we will add the 2 and the 4/5 together, the negative 2 and the 4/5 together. All right, so what do you get when you have 4/5 minus 2? Very good, negative 6/5. And then what else did we have? Minus 2/5 x. There's one more thing that simplifying, I mean, this would be fine. You can leave it this way. I don't know if WebAssign will take it because there's one other thing that you could do to it. Does anybody know what it is? Okay, so there's two things I heard, and they are both legit things. What did you say, Marco? Yes, maybe that's what I actually heard. I didn't. That's not what I thought I heard you say, but that is exactly the truth. So this is to the power 3, and it's a square root, right? So that means you can pull out a 2 minus x, and you'll leave one of the 2 minus x's underneath, so 2 minus x cubed. Over here, you have the negative 6 over 5 minus 2 over 5x. Any idea what they might do to clean that up just a little bit? They might pull out the 2/5, because there's a 2/5 in both of them. Oh, because I left the cube off by accident. Oh, no, I see what you're saying. I put this one in here by accident. That's what you wanted me to take away. Yes, you're right. It's like, because there's something I messed up by accident, that's why. Okay, so the other thing, again, this would be perfectly fine on a test, no problem with that. You might actually see them pull out the 2/5, a negative 2/5 even. So this would be 2 minus x. You might move the factor in front, so this would actually then be a 3 minus x, and then a square root of 2 minus x, some version of that. Huh? Yeah, we lost the c somewhere along the way. We should probably go back and put that in. Look at that. Erasers work great. That's what happens when you switch slide screens too frequently. You lose stuff. Any of those versions would be fine, but it did start out in radical form, so it needs to end in radical form. Okay? Y'all good with that? Okay. I think we have 2 more, and I think they actually have the slides for these in here. 7 and 8. How are 7 and 8 different than the ones we've done before so far today? What's different about these? It's not the radicals. We already did something with radicals. It's got the numbers on the top and bottom, right? There's limits of integration. All right, so you guys know what you do with limits of integration. You just plug them in at the end, right? And that's what we're going to do here as well. But what we're going to do in the meantime is we're going to ignore them, and we're not even just going to ignore them. We're going to ignore them and leave them off. And here's why. We're about to turn everything into u, right? Yeah? What variable do the 1 and the 9 apply to? X. So I should not have the 1 and the 9 on the steps that involve u because they don't apply to u. They apply to x. So for starters, it might be helpful to think about this rewritten in a different way. What part of this is the inside function? Yeah, this piece right here is u. So if I've got this piece as u, that is, it's 1 plus the square root of x. This piece I can think of as being a separate piece, and I don't want to move it. I really want this to be written and thought of as 1 over square root of x, and you'll see why in a minute. This other piece, it's perfectly fine and legit and helpful even to think of this as being written to the negative 2 power. Because it's going to be u, right? I'm going to put a u right there. I'm going to have a u to the negative 2. But come back over here then to finding the derivative of u. What would du be for 1 plus the square root of x? And if it helps you, you can think about this, of course, as 1 plus x to the 1/2. 1/2, x to the negative 1/2. Let's rewrite that in terms of radicals. What would that look like?
1 over 2 square root of x.
All right, do you see that 1 over square root of x? I know I've got a 2 that I don't like, but the rest of it, that looks like the other piece I have, right? Yes, it does. So again, I don't like the 2, so what am I going to have to do with the 2? Yeah, I need to multiply it to the other side, right? So my 2 du is going to replace dx and the 1 over square root of x. So those 2 pieces are going to get replaced by du. In the middle here I have u to the negative 2. And I have my integral, and notice I do not put a 1 or a 9 on there. Okay, this is important. Does everybody see where all the pieces went? All of this was over here, so it was replaced by 2 du. Oh, I left my 2 off. I haven't get my 2 in there yet. How about a 2 in the front?
Couldn't get the square root of x, or u, in the first part, so the square root of x equals u minus 1.
You mean from like right here, Evan?
Yeah.
You can, but the problem is that the du has to be in there somewhere. So I already have the square root of x in the denominator, this piece right here. I already have that being taken care of when I do my derivative. It's already there. If I had an extra one, I could certainly have an extra, u or something like that involved like I did in the last problem, but I don't need it on this one. What's the antiderivative of u to the negative 2? 2 stays. U to the negative 1, and then over my negative 1, right? And that, of course, simplifies to negative 2 over u. Definitely not done. Issue number 1, I need to replace the u with what it is equal to. U in this problem is equal to 1 plus the square root of x. So the first issue is that I have negative 2 over 1 plus the square root of x. What else do I need to do to finish this problem now? I won't need a plus c on this one. Do you know why? Yeah, because I have that 1 and that 9, and that's my last thing I need to do. I need to go back and evaluate at 9 and then at 1. So I have negative 2 over 1 plus the square root of 9 plus negative 2, I'm sorry, not plus, minus a negative 2, which will be a plus, over 1 plus the square root of 1. So the first one becomes negative 2 over what? 4. The second one becomes plus, and then I've got what? 2 over 2, which is 1. So I have negative 2/4 plus 1, simplifying all sorts of good stuff. What do I get? 1/2. All that work for a 1/2. All right, here is our last example. Evaluate the definite integral. Okay, this one's interesting, and here's why. Part of this you don't need u substitution for, and part of it you do. Which part do you not need u substitution for? Sine of x. So the first thing I want to recognize is that I'm going to separate this problem into 2 pieces. One that's sine x dx, and one that's the cosine of 2x dx. I'm allowed to do that. We had an integral property a couple sections ago that says that that's a totally, that's what we do. We have that ability to do that. The first part we can go ahead and evaluate. What is the antiderivative of sine of x? Negative cosine of x. Very good. And I can evaluate it at pi and at 0. So I'm just going to keep going straight down the left-hand side of this, and then we'll go over to the right-hand side in a minute. So this is negative cosine of pi minus a negative cosine of 0. And if we want to, we can sort of change these two because it's minus a negative. What is the cosine of pi? Negative 1. And I've got a negative in front. So this is negative, negative 1. Plus, what's the cosine of 0? 1. So this is 2. Right? Okay, sort of half the problem done, basically. Now over here on this part, what will u be? 2x. So similar to one we did before with secant squared in it. What would du be? 2 dx, right? So as I'm replacing these pieces, first thing, don't put the 0 and the pi on there, because we're changing the limits of integration to, or we're leaving them off to accommodate the fact that we're changing our limits of integration to be in u. There will be a 1/2 in the front here, because this 2 is missing, right? And then I have my integral of cosine of u du. What's the antiderivative of cosine of u? Sine of u. But I don't really have u. I have 2x. And I'm trying to evaluate it at pi and at 0. So this is now sine of 2 pi minus sine of technically 2 times 0, which of course is just 0. So what is the sign of 2 pi? It's 0. What is the sign of 0? It's 0. So all the second half of this problem results in is nothing. It results in a big fat 0. But it tells us then that the answer to our question was actually the 2. So the total area is 2. Okay, any questions on that? All right.